Hello everyone, welcome to a new lecture. So in this lecture we will study about liquids in rigid motion. So many fluids such as your milk or gasoline are generally transported in tankers. And in a acceleration tanker, what happens? The fluid rushes to the back and some spacing occurs. Okay, but then a new surface is formed. Your each fluid particle is assumed to have a same acceleration. Like if you say there is a container, let's say this is a container and we have filled this container with water. Let's say this is your level of water. Okay, and if I accelerate it in this direction A, then the surface changes slightly. Okay, so this becomes free surface. Each and every particle inside the liquid have the same acceleration A in forward direction. Okay, now this entire fluid moves like your rigid body. Okay, now that like if it makes this shape, so in this shape it moves in this shape only, like is a this entire thing is a rigid body. Okay, now here as I mentioned acceleration, let's say that your acceleration is equal to 0. So like if it is a uniform velocity, in case of uniform or constant linear velocity, linear velocity velocity, like there will be no change in fluid level surface. Okay, fluid surface, I can say fluid surface. Okay, so if I say your A is equal to 0, so your water or your fluid surface will remain straight as what it is at rest. Okay, so at rest or your constant linear velocity, there is no acceleration available. In that case, your fluid will fluid level will remain horizontal. But if there is some certain acceleration, then what will happen? Your level of the fluid or like your fluid surface will change. Okay, okay, now like what happens here now? If there is acceleration, so due to this acceleration, what will happen? There will be pressure or force acting on the on these walls. Okay, okay, so like your initially your pressure distribution at this point, this side and this side, both sides are same, but due to the acceleration, presence of acceleration A, what is happening? Your pressure distribution changes. I hope you get this point. So as I mentioned that this entire liquid will act as a rigid body. Now what I can say, like since it is like it will act as a rigid body, and we can say that there won't be any relative motion. No relative motion between particles. Particles. Oh sorry. Particles. Okay, and of course particles of fluid. No relative motion between particle of fluid. Therefore, if there is no relative motion, there is no shear stress. No shear stress. Okay, so your fluid pressure at all different wall will change, and we can calculate the distribution of the pressure. Okay, now as because of these, it is called your rigid body motion. Rigid body motion. Okay, so this rigid body is in motion with an acceleration of A. Okay, so there are two type of rigid body motion. First is your translation, second is rotation. Okay, two types of rigid body motion. First is your translation. Translation motion. Second is rotation motion. Like this example I have discussed is for your translation motion. So for rotation motion, let's consider if this or a different, let's say cylindrical container. Let's say there is a cylindrical container and the cylindrical container was rotated about the central axis. What will happen? Your initial water surface will become something like this. Okay, and this volume here becomes your rigid body. Okay, there won't be any relative motion between these two fluid particles now. This is your example of rotational motion. Now we will start our first topic, that is your rigid motion, rigid translation motion. Rigid translation, translation motion. Okay, now let's consider a fluid element. Okay, so say that we have a fluid element of rectangular shape. Okay, so let me draw it here first. So let's say that this element does have your dimension, that is your length of dx. Dx. This dimension is dy. This dimension is dz. Okay, so this is the dimension of your this rectangular element, and at the center of this element, let's say this is a point. At this point, your pressure is P and is a function of x comma y comma z. Okay, and one more thing, let me mention your coordinate axis here. So your coordinate axis is like this. This is x direction, this is y direction, this is the direction z. Okay, and one more thing, let's say that the acceleration for this element in x direction is given by ax, or let me write it here. This is your ax. Dimension acceleration in y direction is ay, and this is your ay. Okay, this is your az. Okay, no, sorry, y, and this is your z. Okay, like I mentioned it here. I think previous it should be y only, and it should be z here, z. Okay, because this dimension I consider dz, so this should be z here. This should be z. This is y. Okay, so we know the accelerations and we know this point. Now let's say that acceleration due to gravity will always be acting in downward direction. This is your g vector. Okay, so what I can say, I can send it due to this presence of this g vector, weight of this element, that is equal to your rho g v, that is your dx times dy times dz, is acting at this point. Okay, okay, okay. So let me like move this further away. Okay, let me write it here. So what else I can say that so I can say from Newton's second law of motion, from Newton's second law of motion, we can say that df vector is equal to delta m times of acceleration vector. Okay, now delta m, as I mentioned earlier, is equal to density times of volume, and volume is your dx times of dy times of dz. This is your dm. Okay, okay, and this delta f is your net force acting on the element. This is your net force on element. And since this body is inside your water, or inside your liquid, this like element is inside your liquid, so there must be some pressure forces acting on the surfaces. Okay, so if the pressure force at this point is p, of function of that is x comma y comma z, then pressure at this point, or at this surface, can be given as your p minus, since like this is a function of z, this direction is a z function, so p minus, as we move downward your pressure will change because we are moving in minus z direction. So I will like write here p minus del p by del z, del p by del z, okay, times dz divided by 2, since the distance between the center point and this surface is z by 2 only. Okay, now this times of this is your pressure, and if I want to convert it into force, I will multiply it by your dx times of dy, dx times of dy. Similarly, if I want to indicate the force on this upward surface, so I can write it as p plus dp by del p by del z times of dz by 2 times of dx dy. These are forces on these two surfaces. Okay, similarly, if I talk about your force on this surface, let's say this surface, on this surface, so I can write it as p. Now we are moving in minus x direction, so I can write p minus del p by del x times of dx by 2 times of your dy into dz, dy dz. Okay, now in this direction, if I want to write force, so this will be your p plus del p by del x times of dx by 2 times of dy dz. Okay, we can also write your forces in your y direction also. So if I want to, but the like your diagram will become very congested, so I won't be writing it here, but that will become like in the your inside direction, like in this direction, it will become p, and since we are in like the forward direction, in direction of y, so I will write it as p plus del p by del y times of del y by 2 times now area is here dx times of dz, dx times of dz. Okay, and similarly p minus del p by del y times of del y by 2 times of del x del z will be your force in this direction here. Okay, but I won't be mentioning this that here. Now What are other force you can think of? Like there might be presence of your shear stress, but here I mentioned that for like since this surface act as a rigid body, so there is no shear stress. So we won't be considering any shear stress here. Okay. So I can start applying your Newton's second law of motion in all three directions. Okay. So what I can write here. So in x direction, in x direction, if I apply my Newton's second law of motion, so I can write that delta force in on the surface in like x direction can be given as, so this is x direction, so this will become p minus del p by del x times of dx by 2, okay, minus opposite force, okay, sorry, I forgot to mention area here, that is dy dz minus, okay, net force in x direction, x direction, this is the x direction, so net force will be force in this direction minus force in opposite direction, minus p plus del p, sorry, del p by del x times of dx by 2 times of dy dz, dy dz, this is your force in x direction. Now if I solve this, so I will obtain my delta fx, x direction force will be minus del p by del x times of dx dy dz. So this is your delta f in x direction. Now if I talk about in x and y direction, sorry, y and z direction, so I can write in y direction. Similarly, I can write like in similar way I can write that dfy will be equal to minus del p by del y into dx dy dz. Okay, and in case of your y direction, sorry, in z direction, in z direction, what I can mention, like I can again write the equation del fx is equal to, sorry, z delta f in z direction. Now this will be your this force minus this force minus the acceleration due to gravity. Okay, so like this term will remain same, that is del p by del z times of dx dy dz. This term will be same, and there will be additional term, and that additional term will be your minus, that is weight, that is your rho g times of dx dy dz. Okay, so if I want to write your overall equation, if I want to write your delta f vector, so I can write it as your delta fx I cap plus delta fy j cap plus delta fz k cap. Okay, and if I substitute the values here, so let me substitute these values here, so I will get it as delta fx will become minus del p by del x times of dx dy dz minus del p by del y times of, or let me write it together, so this will become minus of del p by del x times of I cap plus del p by del y times of j cap plus del p by del z times of k cap, okay, into dx dy dz minus, now this weight in k component also, so this is your rho g times of dx dy dz times of k cap. Okay, so this is your total force acting on the element. Now if I substitute this is equal to m times of delta m times of a vector. If I substitute the value of delta m here, so I can write this as, I can write this is your minus gradient of pressure vector minus gradient of pressure vector plus rho g k vector or k cap is equal to minus rho a vector. Okay, so this equation here is your equation for rigid motion, rigid body motion of fluids. In case of fluids, this is your equation for rigid body motion. Okay, and I can further write it as your like del p by del x, this term will also become positive because we have taken minus on this side. Okay, so I can write del p by del x times of I cap plus del p by del y times of j cap plus del p by del z times of k cap or plus rho g times of k cap. Okay, is equal to minus rho times of ax I cap plus ay j cap plus az k cap. So this is your equation here. You can like equate corresponding I values to calculate your equation in your x direction, corresponding j cap values to for your in your motion in or motion in your y direction, and similarly k cap for your motion in k direction z direction. Okay, now for accelerating fluid I can write, for accelerating fluid what I can say from here, I can say that del p by del x is equal to minus rho ax, del p by del y is equal to minus rho ay, and del p by del z is equal to minus rho az minus rho g, or I can write it as minus rho times of az plus g, that is acceleration due to gravity. Now here your g is a special term. Okay, it happens only in your this z direction only. Okay, so these are your ax, ay and az values corresponding to your x and y and z directions. Now I can write here a special case. So let me say, sorry for that. Now let me write here case 1. Now case 1 assumed to be fluid at rest. If your fluid is at rest, so what will happen? Your ax will be equal to ay will be equal to az, and all three values will be your 0. Okay, so your what will your equation become? Your equation become del p by del x is equal to 0, your del p by del y equal to 0, and del p by del z becomes your, from here we will see, so this will become minus rho g. So this here is what we have obtained called your hydrostatic law. Hydrostatic law. Okay, you have read equation na in your fluid measurement chapter, that del P by del Z is equal to minus rho g, or del P by del S is equal to rho g. Okay, so this here is your equation. And if I talk about, let's say, let's assume another case, that is case 2. So case 2, let's talk about, in case 2, free fall of a free fall of fluid body, of fluid body. Okay, so in this what will happen, we can say my ax is equal to 0, ay is equal to 0, but your az value will be equal to, az will be, like it is in downward direction, so this will become minus g, minus g. Okay, so this is your special value here, az will become minus g. Now if I substitute the value, so I will obtain del p by del x is equal to del p by del y is equal to del p by del z is equal to 0. Okay, so all terms become 0 here. Okay, so from here what we can say, from here we can say, for a fluid in free fall, I can say that for a fluid in free fall, pressure throughout the system is gauge. Okay, so like we see that there is no variation in pressure with your depth. Okay, with height there is no variation in pressure, so your at your each and every point your pressure will be equal to your gauge pressure. Sorry, like not gauge, your outside pressure. Okay, so gauge pressure, the pressure throughout the gauge system is atmospheric, is local atmospheric, that is your gauge pressure becomes 0, p gauge will become 0 at each and every point. Okay, now let's consider that your container. So this is your acceleration on straight path. Acceleration on straight path. Okay, so let's consider a container. Let's say that this is the container here. Let's wait a minute. So let's say that this here is your container. Okay, and this container is originally, this is your, let's say, level of water or liquid level, initial level, liquid level. Okay, this is your initial liquid level. Now what is happening is that, let's say that this particular container is accelerated, and let's say it is accelerated in this direction. This is your a vector. Okay, so what we can do, we can like take the components in two direction, so here and here. Okay, so this will become your az, and of course in this is your az and this is your ay. Okay, in vertical direction it is az, in horizontal it is ay. Okay, so from here sorry, this is your x. Okay, x and z. Okay, now From here, what we can write? We can write that if pressure at any point, let's say at any point, if I talk about pressure, so pressure at any point can be written as pressure is a function of x comma z. Okay, or I can write pressure is a p of x comma y. I can write it like this. See, this is your p. Okay, now if I differentiate it, so I can write that for a small change dp can be written as del p by del x times of dx plus del p by del z times dz. Okay, so here we know the case that your del p by del x is equal to your del p by del x is equal to rho ax, and of course with minus sign, and your del p by del z is equal to minus rho g plus ax. So this is your relation between relation for del p by del x and del p by del z. Okay, so if you substitute these values here, so from here I will obtain your dp is equal to, so del p by del x is minus rho ax dx plus, so sorry, minus rho times of az plus y times of dz. Okay, so this relation is your like your pressure at any, so change in pressure between any 2 points. Okay, so like if I integrate it from 1 to 2, so I will get p2 minus p1 here, and this will become x2 minus x1, this will become z2 minus z1, because the x and az will be constant throughout the liquid. Okay, so from here what I can do, like for constant pressure line, if I talk about for constant pressure lines, for constant pressure or isobaric lines, we can say that our dp should be 0. Okay, dp is equal to 0. If you substitute dp is equal to 0, so from here we will obtain our dz by, let me write it this way. Yes, okay, sorry, that is correct. So dp by dx is equal to so dz, so this will become ax upon az plus g, and this is with negative sign. Okay, so this here is your like slope of isobar. Okay, and if both values are constant, so this slope will be constant and the value will be negative slope. So the slope of the free surface would be something like this, something like this, sorry, something like this. Okay, okay, so this will become your new free surface, and this angle will be theta. So from here I can write that tan theta is equal to your slope of free surface, or any, or your constant pressure surface is equal to ax upon, sorry, with minus sign, of course, minus sign of ax upon az plus g. Okay, this is your slope. Now, so if I want to draw your multiple isobars, so I can say that this is your p is equal to p atm here. Okay, this is your line of p1, this is your line for p2. Okay, this is your line for p3. Okay, So this is your P is equal to P1, this is your P is equal to P2, this is your P is equal to P3. So these are your isobars. Okay, I hope you get this. Now let's say that your if, or let's move to next. Okay, let's mention it here only, that if your az is equal to 0, so in that case what will happen? In that case what will happen? Let me mention those points here. If az is equal to 0, so from here you can write your tan theta is equal to minus ax by g. Okay, and if your ax is equal to 0, if ax is equal to 0, so in case of ax is equal to 0, it means there is no horizontal acceleration, so there will be only your vertical acceleration. So in that case you will obtain your tan theta is equal to, this ax will become 0, so this will become 0. It will become like free surface will remain horizontal. Okay, and if I take this equation into effect, let's say that from if I take this equation into effect, so from here what I can write, I can write that my pressure or pressure gradient, if I talk about, so if I integrate this, so this will become pressure is equal to, or I can also write it as like this as del p by, instead of g, if I write h, so I can write it as equal to rho times of g plus ax. Okay, so from here I can write that my pressure at any point inside your accelerated vessel is equal to rho. Now here g will become g effective times of h, and where your g effective is rho times of g plus, so this is your az. Okay, az times of your h. Okay, so if your like acceleration is upward, your body is accelerating in upward direction, so your az will be positive. If your body is accelerating in downward direction, so your az will be negative. I think I don't need to tell you these things. Okay, and this is your p gauge. Okay, p gauge. I hope you get this point. Okay, now one more little thing I would like to add in here, that when we talk about your accelerated vessel, let's say like this, take this example. So if free surface will change, so after some acceleration, so from here we will see that your this is proportional to your ax. So if larger the value of ax, let's say your az becomes 0, so your tan theta becomes directly proportional to your ax. So if ax value is very large, so what like if we keep on increasing the value of your ax, so in that case what will happen, your this slope will like keep on being slant. Okay, so a point will come at, let's say at this point, when it reaches this point, what will happen, your free surface will be something like this. And just if we increase the acceleration of the vessel by small amount, so it should like your water will spill from inside the vessel. Okay, so in that case what we can do, or if we talk about, let's say just up to like your water is not spilled, up to that case what would happen? Let's say that this distance here let's say is a, and this distance is, let's say, b. So change from your initial level. Okay, so like if I talk about since no water is spilled or no liquid is spilled, it means that the volume initial is equal to volume final. So from here what I can say, that this about this line, this area should be equal to this area. I hope you get this point. Okay, so if both areas should be equal, And since this point lies on your midpoint, so from here we obtain your A is equal to B. It means that rise in fluid level on on one side is equal to fall of fluid level on another side on another side. Okay, because your volume of the fluid remains same. Now if there is a case of spillage, so in that case you will assume an indicated surface or sorry I mean imaginary surface like this. Let's say it should be like this, but what will happen, that actual amount will be like this, actual amount will be like this. So in that case what we can do, we can calculate the change in the volume. Okay, that will be the volume of spillage. Okay, now since I have there is like a rise in the one side pressure at sorry height of the liquid at one side, and there is fall at another side, so there will be some pressure distribution. So in this part let me tell you about the how the pressure is distributed. Okay, so if I talk about pressure distribution, so in this figure only I would mention what will the pressure distribution. So first let's remove these lines and also this line. Okay, so this is your actual case. Okay, now let's say that if this size height is h1, if this height is, let's say, h1, let's say this is your reference line. Okay, now we can say that here up to here your height is, let's say, h1, or better let me mark it somewhere. Okay, so let me mark it here. So this distance is your h1. Okay, now similarly this distance is your h2. Okay, and if I talk about your pressure distribution on both sides, so at this point your pressure will be again be 0, or gauge pressure will be 0, and it will keep on pressure will keep on increasing. Okay, and at this point, at your reference point, let's say this is your pressure. Now pressure at this point will be rho g, and g will be g effective times of h1. Okay, and this is your pressure distribution. Okay, and on this side this will be a pressure distribution. Okay, and this is your pressure distribution on this side. So at this point your pressure will be rho g effective times of h2. Okay, this is your pressure distribution. Let me move it into the center first, and I would like to show one more point. Like if it is asked what is the force on both walls, so we know that from your last chapter, that is sorry, last to last lecture, that was your force on the your surfaces, hydrostatic force on the surfaces. So from there we can say that is some force F1 will be acting here, F1, and some F2 force will be acting in this point. Let's say this is point force F2, and we can calculate using your same relations. We can also calculate your value of this F1 and F2. That is, your F is equal to rho g a times of h bar. Okay, and your distance of from the piece from this point to distance for fp, that is hp, height of center of pressure, is your h bar plus I divided by I about your gg, center of gravity, okay, or your central axis, divided by your area times of h bar. So this is your center of pressure, height of center of pressure, or depth of center of pressure from the free surface. Okay, so this is how we calculate your forces or pressure on the wall. Okay, and this F1 minus F2 we can write as it is. We write F1 minus F2 is equal to m times of acceleration. Okay, I hope you understood till this point. Now after this we will start our second part of the chapter, that is your rigid motion, rigid rotational motion. Here up to here we have studied your rigid translation motion. Okay, so this is your topic, rigid translation motion. Now we will start for rotation motion. So this topic is your rigid rotational motion. Okay, and in this case, as I mentioned earlier, we will be considering a cylinder. Let's say again that let me or let's say that this is your cylinder. Let me make it small. Okay, and what we have done, we have attached it to a axis, and let's say that your axis is this is your axis, and we are rotating the cylinder about this axis, okay, at an angular speed of omega, and this axis is your z axis. Okay, and initial free surface of your body's initial free surface, let's say this was your initial free surface, okay, this is your initial free surface. But what happens when we start rotating the surface? It becomes like this. Sorry. So this is your this will be your final surface, will be something like this. Your liquid will be like this. Okay, and let's say, so in this case, what will with the some standard figure terms, let me write it here. So we can consider here either your elements, consider your cylindrical element, and we can study the force distribution on this on that. We also know that here each and every particle will be going a circular motion. Okay, and we know that for circular motion your centripetal acceleration is given by r omega square. So I can write that your from your translation equation only, if I convert convert it from Cartesian coordinate to cylindrical coordinate. Okay, so I can write that dp by dr is equal to your rho r omega square. Okay, and this centripetal acceleration is in inward direction, hence your minus sign will not be here. Okay, rho r omega square. And if I talk about your del p by del y, so del p by del y is equal to 0, and del sorry not y. Okay, and not y, this should be theta. Okay, we are talking about your rotational motion. Okay, and this is z, r theta z is equal to rho times of g. Okay, and this g will still be acting in minus negative direction. This is like this. Okay, and we are taking z from this point. From this point, if we move upward, so this is your z. So if I can say that pressure is a function of your r and z. Okay, because pressure is independent of theta. Okay, now from here I can write dp is equal to del p by del r into dr plus del p by del z into dz. Okay, now substitute the values here. So dp is equal to we get it as rho r omega square dr plus minus rho g dz. So this equation, or let me write it different color. So this equation is your rigid rotational motion equation. Okay, so this is the most important relation which is used here, or which will be used here frequently. Okay, now if I want to calculate your isobars, so for isobars I can substitute your dp is equal to 0. So from here I will obtain your dz by dr is equal to r omega square by g, or we can written as v square by r. Okay, basically we will go with this relation generally, but I can write v square by r here, because r omega is equal to v. Okay, sorry, like v square by rg. So let's leave it to this point only. Okay, so dz by dr is equal to r omega square by g. So this is your slope, this is your slope of isobars. Okay, so all we can say that it is your slope is directly proportional to r. Okay, I mean like if we moved from here, if we moved from the axis, if we moved further away, so your slope will keep on increasing in that proportion only. Okay, and if I let's do one thing, let's integrate this term first. So if we integrate this, so from here we will obtain z2, or I can write it as z is equal to r square omega square by 2g, r square omega square by 2g plus some constant. Okay, so from here I can say that my height of the of a constant pressure surface is your direct proportional to r square. So it means that your isobars are parabolic in nature. Okay, I hope you get this point here. Okay, so from this equation we can write one thing. We know that at your r or your z is equal to, let's say this is your z1, let's say that this location is your z1, and this location let's say is your z2. Okay, so at z equal to z1 we know that your r is equal to 0, At z equal to z1, you like this surface is starting to form. So if I substitute this here, so from here I could obtain your z1 is equal to 0. Sorry, z1 is equal to c. Okay. Now, if I also know that z is equal to z2, at z is equal to z2, your r is equal to capital R. So I can write that my z2 is equal to r square omega square by 2g plus c. Okay. So if I talk about, let's say this is, we know that this is your parabolic surface. Okay. And if we say that this is your, this distance is your h, this is your maximum height difference. Okay. If we talk about maximum height difference, so maximum height difference is your h is equal to z2 minus z1, z2 minus z1. Okay. And that will be equal to, h is equal to, if I do z2 minus z1, so only this term will be left, r square omega square by 2g. Okay. So this relation is very important relation in this your rigid rotational motion. And with this equation we can calculate the height of your like this surface. Okay. And your one more point you should remember here, that volume of your paraboloid. So paraboloid is a surface that is formed here. So this volume is your paraboloid. So volume per paraboloid is given by pi r square h is the volume of cylinder divided by 2. Okay. So this is a volume paraboloid. So if you have to like apply volume conservation, so initial volume we know, you know that this will be a cylinder only. Now for final volume we will consider your height of cylinder up to height z2 minus volume of this paraboloid. Okay. So from here we can calculate your, from here we can calculate that required dimension. Okay. Either like we can calculate your value of z2, or if we know the value of z2, so we can calculate the value of h. Okay. So whatever we don't know, we can calculate the unknown term from here. Okay. Now this we can also use this relation, like I told you, to calculate your omega, speed of rotation of the container. Now let's say I want to calculate your pressure at the bottom. So here uh, let's say that pressure at bottom of or bottom surface, pressure at bottom surface in rotating cylinder. Okay. So if I talk about your pressure at this point, pressure, let's say this point, we are talking about the pressure at this point, so I will use this relation only. Okay. That is your dp is equal to rho r omega square dr minus rho g dz. Okay. But at bottom, so this term will become 0, because z at bottom is same. Okay. Or at any level we are talking about. Okay. So from here I can write that my dp is equal to rho r omega square dr. So if we integrate this, so I will get your p2, or like pressure at any point, is equal to p is equal to rho r square omega square by 2 plus some constant. Okay. So this is your pressure at the bottom of your rotating cylinder. Now if I want to calculate, let's say, value of c, so I can say that at r is equal to 0, that is center, your fluid will be in static motion. So at static, like since it is r is equal to 0, so like all point will be static. So at that point we can say that my pressure will be equal to your rho g z1. Okay, rho g, z1 is the height at this point. Okay, so we will substitute this value here. So from here I can write that by c is equal to your equal to rho g z1. Okay, so your pressure is equal to rho r square omega square by 2 plus rho g z1. So this is your pressure of equation at bottom of your cylinder.